So, hello, dear students. Welcome you all to this session. So, in this session, we are going to discuss the AIET 5 Class 11 JEE solutions for chemistry. Okay, so we are going to solve some important questions and some of the questions which you feel very difficult. Okay, so let's start with the first question. So, here is the first question for you on the screen. So barium chloride and sodium phosphate react according to the equation. Okay. And if 0.5 mole of barium chloride is mixed with 0.2 mole of sodium phosphate, how many moles of barium phosphate are formed? So it's very easy, right? But important. So here you can see that 2 moles of sodium phosphate is reacting to give 1 mole of barium phosphate. Got it? So 2 moles of sodium phosphate gives 1 mole of barium sulfate in the given equation. Okay. Now in the question they are asking if 0.2 mole of sodium phosphate is reacting, then how many moles of barium phosphate will be produced? So it is very clear from the equation that even though the number of moles of both barium chloride and the sodium phosphate are given, and I am telling that we have to take moles of sodium phosphate. Why? Because sodium phosphate is the limiting reagent because it is present in very lesser amount, right? The one which is present in lesser amount in the reactant is called as limiting reagent, right? So that limits the reaction. So in the reaction, you can see that 3 moles of barium chloride is reacting. So 3 is bigger than 2, right? So the one which is present in very lesser amount in the reactant is called as limiting reagent. So that determines the amount of the product that is being formed. Okay. So here, since sodium phosphate is present in 2 moles, so it is present at lesser amount. So sodium phosphate is the limiting reagent for the reaction. So with respect to sodium phosphate, we are solving this question. Got it? Now 2 moles is giving 1 moles, and if 0.2 moles of sodium phosphate is reacting, then how many moles of barium phosphate would be produced? So 2 gives 1 and 0.2 gives 0.1, right? So 0.1 mole of barium phosphate would be produced from the given reaction. Got it? So very easy, such an easy question. Just you have to find out the limiting reagent by seeing the reactant number of moles, and then straight away you can get the answer without doing any calculation. Okay, so the answer will be 0.1. Okay. Okay, let's move on to next question. Calculate the mass of 3.011 into 10 to the power 23 atoms of hydrogen. So here the atoms of hydrogen, that is the number of particles, is given to us, and we are asked to find out the mass of this particular atoms of hydrogen. Okay, so we know that in 1 gram of the substance, in 1 gram of the substance, Avogadro number of atoms would be present, right? So what is the Avogadro number? It is 6.022 into 10 to the power 23 atoms of hydrogen would be there. Got it? Now, here you can see 3.011, which is nothing but the half of the Avogadro number. If we divide this Avogadro number by 2, if we divide this Avogadro number by 2, we will get 3.011 into 10 to the power 23 atoms. Okay. So, what is the number of grams? What will be the mass? If it is 1 gram, Avogadro number. If it is half of it, then it is 0.5 gram. Got it? So the mass of the hydrogen for given atoms is 0.5 gram. Got it? So the answer is option D. Answer is option D. Again, it is an easy question. Got it? Now moving on to the next question. Question number 41. So three different equations are given to us, and the delta H value, that is the change in enthalpy value, is given to us. So you can see all the reactions are exothermic in nature because all the values are given in terms of negative. Okay. Now we have to find out the heat of formation of KOH in kilocalories. So to get the formation of KOH, first of all, we have to rearrange the equation. Got it? So first equation remains as such. Let me write the equation. H2 plus half O2 is giving H2O. Okay. So this remains as such, and the delta H value for this particular reaction is minus 68.39 kilocalorie. Okay. And in the second reaction also you can see potassium is reacting with the water H2O to give the aqueous potassium hydroxide, and half of hydrogen gases evolve, and the change in enthalpy for this reaction is minus 48 kilocalorie. Okay. Now in the third equation you see the same aqueous potassium hydroxide is formed. So what we have to do? We have to just reverse, because we need to find out the heat of formation of KOH only, not for aqueous KOH. Okay. So just reverse the equation 3. If you reverse it, you will have KOH in aqueous state. Here also it is in aqueous state. So it gives the solid KOH plus water. Okay. So here, since I have reversed the equation, I have to change the sign of delta H. Now it becomes plus 14 kilocalorie. Okay. Now you just cancel out the common terms which is present in both the side, both left hand side and right hand side. So who are the common terms? H2 is common, so we can cancel out that. KOH aqueous is common, so cancel out that. And here we have 1 moles of H2, and here half mole of H2 is there. So remove this half, and from 1 if I remove the half, I'll have half H2 here, and what else can be removed? So that's all, right? So just write the reactant. In the reactant side we are having a potassium and a half mole of H2 and half mole of O2 is there in the reactant side, and in the product side we have the KOH. Okay. Now this is the reaction. So we have to find out the heat of formation of KOH from this reaction. So what we have done, we have just added all the three equations. We have just added all the three equations and cancelled the terms, common terms, right? So just you add all the three delta H values, that is delta H1, delta H2 and delta H3. So just add all the three, you will get the final delta H for the formation of KOH, which will be equal to H1 plus del H2 plus del H3. It is nothing but minus 68.39 minus 48 plus 40. Okay, so where it is given in option B. So option B is the correct answer for this question. Got it? Clear? So for the solid KOH, we are finding out the heat of formation of the solid KOH, not for aqueous KOH. Okay. So I hope this question is clear to all of you. Now let's move on to the next question. That is question number 42. So here the bond enthalpies of hydrogen, chlorine and HCl are given to us. Okay. And we have to find out the enthalpy of formation of HCl. So here again the delta H formation of HCl has to be find out. Okay. So here to find out the delta H formation of HCl, we need to write the reaction first. Okay. So as you can see here, enthalpy of formation can be written only for the formation of 1 mole of the product, right? So for the formation of 1 mole of HCl, 1 mole of HCl, half mole of H2 will be reacting with the half mole of Cl2. Okay, both are in the gaseous state. So 1 mole of the substance is now formed from its constituent atoms, and for this reaction only we can write the enthalpy of formation. Got it? So now here the hydrogen bond is broken down. That is half HH is there, and that will be broken down. That is nothing but the bond energy. The energy required to break the HH bond is nothing but the bond energy. And because of this bond breaking process, we are getting the hydrogen atom. Okay. And from the same chlorine, so here we are having Cl bond, and if we break that, we will get Cl in gaseous state. Got it? Now this hydrogen and Cl, they react with each other to form the HCl. They react with each other to form the HCl. Now here the bond is formed between the two atoms. So it is a bond formation process. So what happens? So the delta H value will be negative. So that is minus, you will have minus 431. Okay. So that is minus 431 we can take. Got it? Now we have to find out the delta H of formation. Delta H of formation, right? Delta H of formation. So it is nothing but the standard enthalpy of or bond energy of the reactant minus delta H of the bond energy of the product. So already I have taken this product in terms of negative. So you can just directly substitute that. So who are the reactant? Hydrogen and chlorine are the reactant, right? So just they are in half moles. So what we have to do? Just take out the half out, then substitute the remaining values, that is 435 plus 243. So this is your reactant value, and minus 431 for the product. 431 for the product, kilojoule per mole. Okay. Now on solving this, we will get minus 92 kilojoule per mole. Minus 92 kilojoule per mole. So that will be the answer. Okay. So the answer is option B. Answer is option B. So you can take a delta H is equal to this, or I can write. So it is also written as, so the negative of the bond energy of HCl. Okay. Like this also I can write. Clear? So the final answer will be minus 92 kilojoule per mole, and we are studying this equation. So we are calculating the standard enthalpy from the bond energy values, that is reactant minus product. Got it? Yes. Now coming to question number 44. So it states that 50 ml of water takes 5 minutes to evaporate from a vessel on a heater connected to an electric source which delivers 400 watt. The enthalpy of vaporization of water is, and given the density of water is 1 gram per milliliter. So here we have to find out the enthalpy of vaporization of water, which is nothing but delta H of vaporization. So this we have to find out. Okay. Now what are the things given? Time is given, volume is given, and 400 watts, which is nothing but the power, right? So the power is equal to 400 watts. Okay. So one watt is equal to 1 joule per second. So in terms of joule per second, we can write 400 joule per second. That is the work done in 1 second is equal to 400 joule. So the same way, if for the work done in 5 minutes, because the time is given here in terms of minutes, right? So the work done in 5 minutes. 5 minutes, how many seconds we have in 5 minutes? So 1 minute contains 60 seconds and 5 minutes contains 300 seconds. So the work done in 300 seconds is equal to 400 into 300, which is equal to 1. It will be 12,000. In terms of kilojoule per mole, it is 120. It is, yeah, it is 1,20,000. In terms of kilojoule per mole, it is 120 kilojoule. Okay. Now, in this 5 minutes, 50 ml of water, which is nothing but the 50 gram of water. Density is given in terms of 1 gram per milliliter, right? So we just substitute there. So in 5 minutes, that is 50 ml, which is nothing but the 50 gram of water is evaporated. 50 gram of water is evaporated. Okay. Now, the molar mass of water. The molar mass of water, we all know it is 18 gram. It is 18 gram per mole, right? So, if the molar mass is 18 gram and if the mass of water is 50 gram, we can find out the number of moles from mass by molar mass formula, right? So the number of moles will be equal to the mass of water is 50 and the molar mass of water is 18. So this is the number of moles. Now we have to find out the delta H of vaporization, right? So it is equal to the work done in 5 minutes, that is 120 kilojoule divided by the number of moles, which is nothing but the 50 by 18. So on solving this, you will get 43.2 kilojoule per mole. Okay. So option B will be the correct answer for this question. Got it? So the work done by the number of moles gives you the delta H, enthalpy of vaporization of water. Got it? So the answer will be option B. So let's move on with the next question. Which of the following is not formed when H2S reacts with acidic K2Cr2O7 solution? So for this we have to write the equation first. So when hydrogen sulfide is reacting with potassium dichromate, that is K2Cr2O7, so it gives Cr3 plus sulfur. So what is the oxidation state of sulfur here? It is -2, and here for chromium it is +6, and in the product side it is +3 for chromium and 0 for sulfur. Okay, so these are the products. So here you can see that chromium is having +3 state and +6 state. Okay, so no other states are possible for chromium. And for sulfur, you can see the oxidation state will be greater than -2 in all the cases. Will be greater than -2 in all the cases. Okay. So for chromium, I told you it can be +3 and +6. No other state is possible. Now, when you check for the options, so in option A, if SO4 is taken as -2, chromium is taken as +2. So +2 state for chromium is not possible at all. +2 for chromium is not possible. Okay, for chromium. So that cannot be the product formed from the reaction. Okay, so that could be the correct answer for this question. And when you check for option B, here the chromium is in +3 oxidation state. And coming to option D, it is sulfur, it is in 0 oxidation state. So they are also given in the product. And coming to this K2SO4, here you can see if I want to calculate the oxidation state of sulfur, it is X, and here +2, and here -8 equal to 0, and X is equal to +6. Okay, so it is greater than -2. So it is also not it is also possible. For sulfur, oxidation should be greater than -2, and here in this compound, the oxidation state is coming out as +6, so that is possible. But in option A, chromium is taking +2 oxidation state, which is not possible. So that's why the compound given in option A is not formed on reaction of H2S with K2Cr2O7. Got it? Yeah. So coming to question number 49. Yeah, this is very easy. We have to find out the IUPAC name, right? So what could be the correct IUPAC name? So for finding out the IUPAC nomenclature, we need to find out the longest carbon containing chain, right? So here in this compound, alkene is given, and alkene should be given the first priority since it is the functional group. So when I start from this, I can go like this. So it is 1, 2, 3, 4, 5. You can go like this also. 1, 2, 3, 4, 5 can also be given because both the chain contains 5 carbon. So you can go in that way also. For more convenient purpose, I am taking this straight chain as the parent chain. Okay. Now to the second carbon, we have the methyl group, and to the third carbon, we have ethyl group. So in the alphabetical order, which comes first? E comes first, right? So the correct answer would be 3 ethyl, 2 methyl, 1 pentene. Double bond is between alkene is between carbon number 1 and 2, right? So it is pent 1-ene or 1-pentene. So it is given in option C. 3-ethyl, 2-methyl, 1-pentene. So here you have to follow the alphabetical listing. Okay. Yes. Now coming to the next question. Arrange the following compounds in the decreasing order of their dipole moment. So dipole moment is represented by the letter mu. It is nothing but the measure of the bond polarity. Okay, measure of the bond polarity is called as dipole moment. Now we don't have any values here to measure that. So just by seeing the compounds, we have to find out the order. So for this, you can use the relation which I am giving here, that is the charge separation can be find out from the electronegativity difference. Charge separation is directly proportional to the electronegativity difference between the bonded atoms. Okay, and in turn it is directly proportional to the dipole moment. So ultimately what we are going to find out, we are going to find out the electronegativity difference between the bonded atoms. Okay, if the difference is very high, charge separation is very high, then the dipole moment is also very large. Okay, now you see the four compounds. In first compound we have carbon nitrogen bond, and here carbon chlorine, carbon bromine, and carbon iodine bond. Now if I have to compare the electronegativities of all the four groups given here, ethyl is common. Ethyl is common for all the, that is CH3, CH2 is common for all the compounds. We have to find out with respect to NO2, Cl, Br and I. Okay. We all know that the first electronegative element in the periodic table is fluorine. The second most electronegative is oxygen. Third most is nitrogen and chlorine. Right? Nitrogen and chlorine both are having the same electronegativity value, which is 3, but nitro, here in this nitro group, nitrogen is bonded with the two more electronegative atom, that is oxygen. Okay, so this nitro group would be having the more electron withdrawing nature. So the charge separation will be very, very high in this case, and the dipole moment will be very, very large. Charge separation will be more, so dipole moment is very large. That is delta plus and delta minus, charge separation is very high. So dipole moment is also very high. Got it? Now coming to chlorine, bromine and iodine, we know that electronegativity on moving down the group decreases. So who is having the highest electronegative value? Chlorine. So the carbon chlorine bond is more polarized. So delta plus and delta minus. So bond is more polarized because of more electronegativity difference between carbon and chlorine. Charge separation is more. So dipole moment is more. Then comes our bromine. Then comes our iodine. So compound 1 is more polarized. So that is having the highest dipole moment. So 1, 2, 3, 4. So option D is the correct answer for this question. Okay. Now moving on to the next question. Question number 52. The total number of enolizable hydrogen atoms in given compound is. So the enolizable hydrogen can be found out from the total number of alpha hydrogen present in the compound. So the total number of alpha hydrogen you have to find out. So that is the number of enolizable hydrogen. Okay. So the C double bond O is here. So this is C double bond O. We have 3 C double bond O. The carbon which is adjacent to C double bond O is called as alpha carbon. And the hydrogens which are attached to that alpha carbon, they are enolizable hydrogens. Okay. So to this first C double bond O, 2 alpha carbons are there. And to this carbon, 2 hydrogens are there. And to this carbon, 1 hydrogen is there. But only these 2 hydrogens can undergo enolization. So this hydrogen cannot undergo the enolization because it is in the bridged position. You can see carbon is in the bridged position. So that hydrogen cannot undergo enolization. Okay. So here 1, 2. So these two alpha hydrogen can undergo enolization. And coming to the second C double bond O, so both are alpha carbon, and here you have two alpha hydrogen, and here we have one alpha hydrogen for this C double bond O. So totally 5. 1, 2, 3, 4, 5. Okay. And for this particular carbon, you can see here is one hydrogen, and with respect to this carbon, this is also alpha. So it is again an enolizable hydrogen. So totally we have 7 enolizable hydrogen. Totally we have 7 alpha hydrogen which are enolizable. Okay. So coming to question number 53. A sample of aluminium has a mass of 54 gram. What is the mass of the same number of magnesium atoms? So you can see that the atomic mass of aluminium is 27 and for magnesium it is 24. But a sample of aluminium has a mass of 54 gram. Okay. So 1 mole of aluminium contains 27 gram and 2 moles of aluminium contains, that is 2 into 27, which is nothing but 54 gram. Okay. Now what is the mass of the same number of magnesium atom? So they are asking the number of magnesium atoms at the same moles, that is 2 moles. So 2 moles of magnesium would contain 2 into 24, right? So it is 48 gram. It is 48 gram. The answer is 48. Okay. Now coming to question number 54. If 1 decimeter cube of a gas weighs 2.5 gram at STP, its gram molecular weight is. So here 1 decimeter cube weighs 2.5 gram. Okay. Now we know that 22.4 decimeter cube weighs 22.4 into 2.5 divided by 1. So it weighs 56 gram. And we know that 1 mole of the gas at STP, 1 mole of the gas at standard temperature and pressure condition occupies 22.4 decimeter cube. Okay, 1 mole of the gas at STP occupies 22.4 decimeter cube. Now, molecular weight is nothing but the weight of 1 mole of the gas, right? Molecular weight is nothing but molecular weight is the weight of 1 mole of a gas, right? So what would be the answer? So the weight is 56 gram. So the weight is 56 gram. Clear? So 1 mole of the gas occupies 22.4 decimeter. For 22.4 decimeter, the gram is 56. So molecular weight is nothing but the weight of 1 mole of the gas. So the answer is same, 56 gram. Okay, that is a gram molecular weight for the given substance at STP. Answer is 56 gram. Okay. Now coming to question number 55. 1 mole of potassium chloride, that is KClO3, is thermally decomposed and excess of aluminium is burnt in the gaseous product. How many mole of aluminium oxide are formed? So to solve this question, we need to write the equation first. That is KClO3 is undergoing decomposition reaction. So it would give KCl plus O2, right? If I have to balance this, 2 KClO3 will give 2 KCl and 3 O2. This is the decomposition of potassium chlorate, that is KClO3. Now this oxygen, okay, this oxygen is reacting. It is reacting with excess of aluminium. what could be the reaction? So 3O2 is reacting with excess of aluminium, that is 4Al, to give Al2O3. So if you balance this, you will get this kind of equation. So the oxygen which is formed from the decomposition, that is 3O2, is reacting with excess of aluminium. So 3O2 plus Al gives Al2O3, and on balancing you will have 4Al and 2Al2O3. Got it? Now this is the reaction with excess of aluminium of O2. Now we have to find out 1 mole of potassium chloride, decomposition of 1 mole of potassium chloride. So 1 mole of KClO3 will have, so here 2 moles is giving 3 moles of O2, right? If I divide this by 2, I'll get 1 mole of KClO3. So the same way, you divide this 3O2 by 2. So 1 mole of KClO3 would give 3 by 2 moles of oxygen, right? Now, this 3 by 2 moles of oxygen, 3 by 2 moles of oxygen would give, this 3 by 2 moles of oxygen would give 2 by 2 moles of Al2O3, which is nothing but the 1 mole of Al2O3. Got it? So 1 mole of potassium chlorate would give 1 mole of Al2O3. So 1 mole of Al2O3 is formed from the sequence of reaction. Got it? So first we are calculating for the required amount of the compound, and then from that, according to our question, we are finding out for 1 mole. Got it? By dividing with the corresponding number, and here it is 2. Got it? If they are asking you for some other mole, then you have to divide the equation accordingly and get the answer. Clear? Yes. So moving on to the last question for this session, that is question number 60. You have to find the quantum number n corresponding to the excited state of helium plus ion of an transition to the ground state, that ion emits 2 photons in succession with wavelength 108.5 and 30.4 nanometer. Okay, now helium plus ion is there. 2 lambda values are given. So the lambda 1 is equal to 30.4 nanometer. Now in terms of centimeter, it would be 30.4 into 10 power minus 7 centimeter, right? Yeah. Now the second lambda value, that is 108.5 nanometer, which is nothing but 108.5 into 10 to the power minus 7 centimeter. Okay. Now the excited state for helium plus is N2. The excited state, you can see the excited state of helium plus ion can be taken as N2. So it comes from N2 to N1 and from N1 to 1. That is the ground state. So it comes from, first it comes from N2 to N1 and from N1 to the ground state 1. Got it? Now, while coming from N1 to 1, while it is coming from, N1 to 1, so the wavelength, that is 1 by lambda 1, can be calculated from Rydberg constant, that is RH into Z square divided by 1 by N1 square, which is nothing but 1 square, minus the final state, that is N1 square. Okay, now if I solve this, it will be 1 by lambda 1 is equal to 30 point, just a second, 30.4 into 10 power minus 7. Okay, it is equal to, the Rydberg constant value is 109,678 into the atomic number of helium is 2, right? So 2 square into 1 by 1 square minus 1 by N1 square. Okay, now for lambda 2, that is when it is coming from N2 to N1. while coming from n2 to n1. So 1 by lambda 2, that is 108.5 into 10 power minus 7, it will be equal to Rydberg constant 109,678 into the z square, which is 2 square. Here the initial value is n1. Initial value is n1. So n1 square, that is 2 square, because when it is coming from n2 to n1, that is the second orbit, right? So the n1 value will be 2. N1 value will be 2. So in place of that n1 value, you can substitute 2. So the answer will be 1 by 2 square minus 1 by the final state. The final state is n2. So n2 square. Okay. Now on solving this, we will get n2 value as 5. Okay, n2 value as 5, because from this we got n1 value as 2, n1 value as 2 for this, and here n2 value is 5. So hence the excited state for helium plus is the fifth orbit. So we have to find out the excited state of helium, right? And the corresponding n value we have to find out for this particular ion. The n is nothing but the principal quantum number, that is the number of the shell or the number of the orbit, we can say principal quantum number. Okay, so the excited state for helium plus ion is the fifth orbit. It is the fifth orbit. So the answer is 5. Okay. So this is how you have to calculate. I hope this session is very useful for all of you. So thank you for listening the lecture. Okay, meet you all in the next session. Thank you so much.